We understand the primary structure of a protein is the sequence of amino acids. In order to understand the secondary structure, we need to remember that the peptide bond is rigid. There is no rotation between this carbon, nitrogen. This species right here is planar, and it has double bond character. But there is freedom of rotation around the alpha carbon between the carbonyl and also between the nitrogen. When we have an alpha helix, we have to say that every 4 amino acids we will have a carbonyl NH hydrogen bond. I'm going to write it back out here just to emphasize what it is. But it must be between the carbonyl of the backbone of the primary structure, 4 amino acids apart. And in an alpha helix, we will see that the R groups are facing away from the axis of the helix. If I show you a picture that I have from the PowerPoints that you guys have access to, they are available to you. We can represent the backbone with just a plain ribbon. So we see in the ribbon, that will be the alpha helix alone. Then we are also representing how the carbonyl NHs are interacting with one another. When we see the green, these are the R groups that are facing away from the axis of the helix. And then every 4 amino acids, you will have that the carbonyl is interacting with the NH. I have also a much better picture from my organic chemistry textbook that it can also show you that the carbonyl and NHs are interacting with one another by the hydrogen bonds, and that the R groups are also away from the helix. When we look at the secondary structure for the beta pleated sheets, is similar because we will have also that the carbonyls are interacting with the NH, but this one will have, the alpha helix will have a very tight coil backbone, and the beta sheets will have a very extended backbone. What we see here is a beta sheet. This is a turn. We're going to call that a beta turn. And then you see that the interaction between the carbonyl and NH could be in any position in the sequence. So if I make a number, amino acid number 1 can be providing the carbonyl that can make molecular interaction by hydrogen bonding with amino acid that can be in any position of the backbone or the primary sequence. Let's say that it's using amino acid number 40. It's just one example. Let's say that in this position is 40 and that this one is amino acid number 1. That could be a molecular interaction of secondary structure because it's using similar. It's using also the backbone, but it's a very different kind of secondary structure. I also want to show you the picture from the textbook that we have for the secondary structure. Here it is, and it's called the beta sheets, and this one is also coming from my organic chemistry textbook. You guys can see that you can have from any position. It could be one chain with a turn, or it could be 2 chains. You can see that we have carbonyl from one position to an NH in very different position interacting, making a beta pleated sheet. It's called a beta sheet because of the extended backbone. This is a picture from a different textbook. It looks like a folded page, so that's why it's called the beta sheet. That is important for the secondary structure. So we also have that there are no covalent interactions in this case, but how are we going to use covalent interactions for protein folding? We only will use the disulfide bond, that's one that we can do for cross-link of proteins before we discuss the tertiary structure, and that is when you have 2 cysteine amino acids that are providing the free thiol group. So we will have an oxidation reaction. Let's say that this is cysteine and this is a second cysteine. We're going to remove these 2 hydrogen to create a disulfide bond. Other than that, the reactions that we're going to look, the interactions that we need to look for molecular interactions will be all non-covalent interactions. We're gonna have to make a video for that in a minute.